Good morning or good afternoon, everyone. My name is Zhu Meihao from Beijing University of Technology. Today, I will present the paper titled Construction XR Intelligence Management System for Multi-Operator and Multi-Robot Complex Completive Tasks. The central idea of this work is to combine digital twin, extended reality, and intelligence construction. The proposed system is not simple visualization platform. It connects the physical construction sites, virtual simulation, human decision-making, and robot execution. In this report, I will first introduce the research background and gaps, then explain the system framework and key technologies, and finally discuss the prototype validation, effectiveness, results, and conclusions. The motivation of this paper comes from the rapid development of intelligence construction. Construction robots can reduce repetitive, high-intensity, and dangerous manual labor. However, construction sites are highly uncertain, dynamic, and safety-critical. Human operators still play an irreplaceable role in judgment, coordination, and exception handling. The difficulty is to operators and robots perceive and understand the site in different ways. Operators may not fully understand robot data, while robots may not correctly interrupt human intention. Therefore, collaboration only in physical space is not enough. Digital twin and XR technologies provide a way to extend collaborations into virtual space, enabling visualization, simulation, planning, and reserve control. The authors identify three main research gaps. First, the collaboration mechanisms among operators, robots, and multiple robots is still not systematically enough for complex construction environments. Second, many multi-agent collaboration systems come from intelligence manufacturing, but construction scenarios have stronger uncertainty, more temporary changes, and more safety risks. So those systems cannot be directly transferred. Third, the technical pathway for extending construction collaboration into digital twin and XR-enabled virtual space is still limited. Therefore, the objectives of this paper is to design a construction XR intelligence management system with a digital twin core engine. The system aims to support collaborative perception, analyze, and control across physical VR and AR spaces. The slide shows the overall system framework. It can be understood as four-layer closed loop. The first layer is physical space, where operators, robots, materials, methods, and environmental factors generate a multi-source data. The second layer is virtual space, where corresponding digital models are established and updated. The third layer is the digital twin data layer, which stores, processes, and synchronized data from physical and virtual space. The fourth layer is the service system layer, providing decision support, path planning, safety evaluation, defect management, and virtualization. The key point is that the system does not stop at display. It forms a closed process of seeing, analyze, virtual planning, and reverse control. The authors further formalized the system through a 5+3 digital twin model. The model includes physical space, physical subsystem, virtual space, VR subsystem, AR subsystem, service system, digital information, geography, physicals, behavior, and rules. This means that the system is not limited to the geometric 3D visualization. It also includes physical properties, dynamic behavior of humans and robots, and construction process rules. Through one-to-one virtual real mapping, the digital twin represents the current size, state, and supports simulations, predictions, and decision-making. The system is divided into three key subsystems. The physical subsystems includes two types of operators and two types of robots. The on-site operator performs local tasks, while the central control operator coordinates tasks remotely. The managerial robot mainly collects information and supports management tasks, while the operational robot performs specific construction operations. The VR subsystem is deployed in the back-end platform and supports situation simulation, scene reconstruction, task allocation, path planning, and remote interaction. The AR subsystem is embedded in AR headsets and supports on-site operators through task guidance, environmental monitoring, multimodal interaction, and remote communication. Together, the three subsystems form a mechanism based on forward perception and reverse control. A key foundation of the system is the holographic model. The paper describes 5 progressive layers. The 2D model provides drawing-level information such as dimensions, spatial layout, and material specifications. The 3D model builds geometric and physical representations of construction elements. The translate model aligns physical and virtual coordination system. The cloud model supports data storage, sharing, processing, and dispute collaboration. Finally, the holographic model allows virtual objects, tasks, images, videos, and spatial information to be overlaid in the real construction environment. In this way, it becomes the shared information carrier of VR planning, AR guidance, and physical site execution. After the holographic model is established, the system needs practical mapping and interaction methods. The paper processes task panel mapping using the radar view and slate, environmental monitoring mapping using spatial anchors, virtual model mapping through manual makers and tulips, and virtual control panel mapping enabled by hand tracking. For interaction, the authors prioritize gestures because they are natural and relatively robust in construction sceneries. Meanwhile, gates positioning, voice configurations, and WebRTC-based remote video assistance are combined to improve accuracy and reduce operational error. The design makes the system easier to use on-site and more reliable for complex tasks. This slide summarizes 3 management functions supported by the virtual scene reconstruction. For environment exploration, the system combines frontiers and gene-mapping algorithm, DBSCAN collecting, and multi-robot map merging. For safety management, it uses ULO-based target detection, distant analysis, and risk evaluation. When potential human-robot collision risk is detected, The system can provide warning signals and support dynamic adjustment of robot behavior. For quality management, species anchors and point cloud deviations analyses are used to support pre-process, in-process, and post-process control. Therefore, reconstructions becomes the basic for actionable management decisions rather than only a virtual display. Task allocations and path plannings are important parts of the proposed management system. In complex construction environments, multiple robots and operators need to complete different tasks under constraints such as distance, obstacles, robot compatibility, and task priority. The paper introduced algorithms such as k-means, IHHO for task allocations, and PIRT-APF for task planning. The purpose is to generate more efficient target assignment and save robot tragedies. The planned results are then transmitted back to construction robots and AR or VR interface, so the operators can understand, monitor, and adjust the plan. In this scene, path planning is treated as the construction management function, not only a robot control problem. To verify the proposed system, the authors built a prototype and conducted experiments using a scaled cable truss construction model. The experimental environment included on-site operators, central control operators, managerial robots, operational robots, sensors, wireless communication equipment, and XR devices. A holographic model of the cable truss structures was also established as the virtual basis for interaction and management. This case is important because the paper does not stop at conceptual design. It verifies whether the physical subsystem, VR subsystems, and AR subsystem can be integrated and whether the workflow can support collaborative construction tasks in practice. The feasibility verification is organized around several collaborative task scenarios. The first is multi-operators collaborative decision support for model placement. The second is education, training, and assembly demonstration, where AR visualizations help operators understand the process. The third is to detection and management, where virtual annotation support inspections and correction. The fourth is multi-dimensional perception and safety control, using sensors and virtual information to support warning and supervision. The fifth is construction robot environment explanation and path planning. These scenarios show that the system can support operator-robot, and robot-robot collaboration. After feasibility verification, the authors compared the system-assisted method with the traditional manual method for cost and schedule. The earned value method is used. Also, the system have an initial setup delay of about 3 to 6 days. After deployment, it shows lower cost and shorter construction duration. For quality, point cloud scans of the final structure are compared with the design model. The system-assisted method reduces geometric deviations in key components such as the cable trusses, ring beams, columns, and connection points. For safety, a questionnaire survey with 50 participants is conducted, including 25 on-site operators and 25 central control operators. The results show The 65.25% overall support for the system is safety control tasks. To conclude, this paper proposes a construction XR intelligence management system for multi-operators and multi-robots complex tasks. Its main contribution is to combine a 5+3 digital twin model with a physical VR-AR3 subsystem architecture. The system integrates multiple key technologies, including holographic modeling, virtual physical mapping, multimodal interaction, virtual reconstruction, safety and quality management, the task allocation with path planning. The case study demonstrates that the system can improve collaboration efficiency and support multiple management objectives. Future work should focus on reducing communication latency, improving collaborative network architecture, strengthening planning algorithm, and testing the system in more complex real construction environments. That is the end of my presentation. Thank you very much for your attention. I would be happy to answer any questions or discuss the system framework, the digital twin model, the XR interaction design, or the experimental validation in more detail. Thank you.